In our last lecture, we discussed about AC voltage controllers. AC voltage controllers are the controllers which convert one level of voltage into another level. So wherever we require a variable voltage at the output side, we go for an AC voltage controller. AC voltage controllers have a limitation. Those controllers cannot convert the frequency level of the supply. So for the applications where we require the variable frequency at the load side, we go for a different set of controllers which are called cycloconverters. A cycloconverter is basically a device which converts the input power at one frequency to the output power at a different frequency. In some of the cases, we may require the conversion from a constant frequency to variable frequency, and in some cases, we may require the conversion from a variable frequency to a constant frequency. In both the cases, a cycloconverter is a good choice. This cycloconverter, it gives you one stage conversion. That means whatever supply is fed to the converter, through that converter only, you are getting the variation in the frequency at the output side. There are various applications of cycloconverters. Those applications include the speed control of high power AC drives, high frequency induction heating, static VAR compensation, and for converting variable speed alternator voltage to a constant frequency output for use as a power supply in aircraft or shipboards. Now here, if you look at these various applications, you will find that in the first application where we need speed control of high power AC drives, in AC drives generally the power is fed at a constant frequency. However, the drive requires the variable frequency. For that case, the input frequency is fixed. However, the converter is varying. The purpose of using the converter is to vary the frequency. Whereas if you look at the application written at the fourth number, this application suggests that for the power supplies in aircrafts and shipboards, the generator which is used is generally a variable speed generator, and it gives you a variable power supply. The frequency of those power supplies which are used in aircraft and shipboards, the frequency generally received is variable. So there we use a cycloconverter to convert that varying frequency into a fixed one. So both way it can be used. Cycloconverters may be categorized in different ways. However, for the sake of our understanding only, I am giving you a very basic differentiation about the cycloconverters. The very first kind of classification can be done on the level of frequency. If a cycloconverter is enhancing the frequency at the load side, if it is increasing the frequency, then it is called the step up cycloconverter, whereas if it is reducing the frequency at the load side, it is called step down. So for raising the frequencies, we need step up cycloconverter, and for bringing the frequency down, we go for the step down cycloconverters. Now, based on the conversion, there are cases when the supply is single phase and we need a single phase output. So those converters, those cycloconverters are called single phase to single phase cycloconverters. We can have two configurations in this case, midpoint and bridge configuration. I shall discuss these configurations later on. The other conversion can be from three phase to a single phase conversion, or the conversion can be three phase to three phase. So we will discuss all these. So whatever is written on this slide, we'll be discussing all these cycloconverters. Let's first start with the single phase to single phase cycloconverters. In single phase to single phase, we may have the step up operation or we may have the step down operation. Now these are the two circuits which can be used. One is a midpoint construction, another is a bridge type construction. Now both these constructions, both these configurations can be used for stepping up the frequency or stepping down the frequency. So basically it is the firing scheme which is different for step up and step down. Otherwise these two converters are same, or you can say the same converter will give you both the operations for step up as well as for the step down. So let's first try to understand how this converter performs the operation for step up. Now these two configurations, among these two, the very first is the midpoint type. In midpoint cycloconverter, we have the four devices. Basically, we have two sets of anti-parallel connected thyristors. One set is connected here as P1N1, another set is connected here as P2N2. So in this midpoint type construction, we use a transformer which is center tapped at the secondary side. So basically the idea is to convert, because here we need to play with both the halves, the positive half as well as the negative half, and because we need to change the frequency, that is why we are using two sets. If you recall, in AC voltage controllers we used only one set. However, because it is changing frequencies altogether a different game, so we use two sets. While if you go for the bridge type, this bridge type cycloconverter is similar to a dual converter. It uses two bridges. So basically a midpoint type uses four devices while a bridge type uses eight devices. The output and the operation is same. So let us see how the frequency is made to raise, how the frequency is raised at the output with the help of these converters. Let's first try to understand how this midpoint converter works. In a midpoint converter, as I said, there is a center tapped transformer, the secondary of which is center tapped. This is the point where the load is connected. At point A, we connected two thyristors in anti-parallel. At point B, we connected another set of anti-parallel thyristors, and this is the common point for all. So basically, when the supply half, when the first half of the supply is positive, this terminal gets positive, this becomes negative, this becomes positive, and this becomes negative. This makes this polarity appearing at the secondary side. This makes the thyristor P1 as forward biased from the upper group, and from the lower group you can see it is the thyristor N2 which gets forward biased. So that means for the first half of the supply, we can operate thyristor P1 and thyristor N2 because these two are forward biased. Now let's see how these works. During the negative half, what will happen? During the negative half, this point will become negative. So N1 and P2 will become forward biased. So what should be the firing instant? How these four devices are fired? Let's try to understand. This bigger envelope, this one, the complete, let me draw it. This one, this is the input supply. This is the supply which is given at the input side. Now if this supply is given at the input side, its counterpart will be like for P1. If this is the supply, if this red line shows the supply for P1, N1 at this time is reverse biased, N2 is forward biased, P2 is reverse biased. So basically for P1, it is for upper group, it is forward biasing P1 while it is reverse biasing N1. From lower group, it is forward biasing N2 while it is reverse biasing the P2. However, if P1 is forward biased, let us see what happens if we trigger P1 at any instant. If P1 is triggered at any instant, this will be the flow of current that will happen. Now, if instead of firing P1, if we fire N2, what will be the flow of current? The flow of current will be opposite to this case. So in both the cases, the direction of flow of current would be different. So that means by firing P1, the load will receive a current from point A to this point. While if N2 is triggered, the load will receive a current from this point to A. That means the load current will reverse in case of N2 if we are comparing it with P1. So this this positive envelope, it could be said that if this P1 is forward biased and it is giving a positive voltage at the load side, N2, though it is forward biased, but it is giving the negative voltage at the load side. So that means by firing N2, we will get negative voltage at the output side. By firing P1, we'll get the positive voltage at the output side. So this envelope, this another envelope, this shows the negative voltage. However, this red line shows the positive voltage. Now let us see how the firing is done. If at this instant, I am taking the case of this one complete cycle. If we fire P1 at this very instant, what will happen? By firing P1 here, the current in this direction will establish and the load will receive a positive voltage. Now from this point up till this point, that means from this point to this point, we will keep this P1 as forward biased. So P1 is triggered here. As soon as P1 is triggered, the current will establish. We will allow this current to flow until this point. At this point, we will forcefully stop this thyristor P1 from conduction. So at this point, P1 is stopped for conduction. This N2 is also forward biased, but we did not give any pulse to N2. So at this very point, what we'll do is we will give a firing pulse to N2. So as and when we give a firing pulse to N2, the current in this direction is established. So that means we start receiving a supply at the in the negative side. So by firing N2, we start getting the negative output. So N2 is fired here. Up till this point, we keep this N2 on, and at this particular point, we commutate N2 forcefully. So basically in this kind of operation, whenever we require step up operation, we go for the force commutation. So this becomes a necessity for this cycloconverter. Now again at this point, we'll take N2 out from the conduction and we'll again fire P1. Now when again P1 is fired, the again a voltage, positive voltage will start appearing. Again here P1 is stopped, then N2 is conducted, then at this point N2 is forcefully stopped, then P1, then N2. So basically if we look at this half cycle, what we got is we got this as the first cycle, then we got this as the second cycle, then we got this as the third cycle. So that means in one cycle, in one half cycle, we got three cycles, 1, 2 and 3. Now what happens when the second half of the supply comes? During the second half of the supply, this thyristor N1 becomes forward biased from the upper group, and this thyristor P2 becomes forward biased from the lower group. So what we'll do at this point, we will give a pulse to P2, and we will allow this P2 to conduct from this point to this point. So basically here P2 will conduct from this point to this point. And at this point, what we'll do? At this point, we'll forcefully stop P2. And since N1 is forward biased, we'll give a pulse to N1. And then from this point to this point, between these 2 points, we will allow the supply to pass through N1. Then again P2, then N1, then P2, then N1, and so on. So by alternatively switching these devices, we can get another 3 cycles, 2 and 3. So basically if you look at the output side, in one cycle, in this complete cycle, in this I'll draw it again, in this complete cycle, this is the one cycle of the supply side. Now in this one cycle, we got the first, second, then third cycle, then fourth cycle, then fifth cycle, and then sixth cycle. So basically in one cycle we got these 6 cycles. That is why I said, I have written at this side that output frequency f naught is equal to the 6 times of the supply frequency. So basically you have stepped up the frequency by 6 times. So if the input frequency is say 50 hertz, you will be getting 300 hertz at the output side. Now this is what we discussed for the midpoint kind of configuration. We will get the same output, but the firing of the thyristor will be different if we are using a bridge configuration. Let us see how we get this output for a bridge configuration. For a bridge configuration, this is the circuit that is used. Now for this circuit, you can see when supply side is positive, P1 and P2 will be forward biased. When supply side is negative, P3 and P4 will be forward biased. So basically, P1 and P2 will be forward biased. P1 and P2 will be forward biased from 0 to pi. And P3 and P4 will be forward biased from pi to 2 pi. Now, this is the P converter. Now, if we look at the N side converter, during positive time, during the first half cycle of the supply, the positive half of the supply, these two thyristors N1 and N2 will be forward biased. That means from 0 to pi, N1 and N2 will be forward biased, and from pi to 2 pi, N3 and N4 will be forward bias. So let us see how these devices are fired. If we fire at 0, if we fire P1 and P2, we'll get this part. We'll get this part. Now at this point, if we forcefully stop P1 and P2 and allow N1 and N2, then we'll get this part. Then again P1, P2, N1, N2, P1, P2, N1, N2, then P3, P4, N3, N4, P3, P4, N3, N4, P3, P4, N3, N4. So by switching these devices in the bridge configuration, we can get the similar output. Here also in this case, the output frequency is 6 times of the supply frequency. So basically the output is same. The only thing is here we are firing these two devices simultaneously, and in midpoint midpoint converter we were firing these single devices. In this, although we are using a large number of devices, but the transformer utilization is better in this case, and this gives this bridge configuration, it gives a better control. You will get to know how this bridge configuration is better than kind of midpoint configuration, and in most of the cases we use the bridge configuration. Let's try to understand how we get the step down operation. As I said earlier, for step down operation as well, the circuit used will be same. So these two are the similar circuits that we have used for the step up operation. Let's try to understand the step down operation with the help of a midpoint converter. Now here, why I'm using midpoint converter first, because it gives you an easy understanding about the topic. Now here, during positive half, P1 is forward biased. So if I fire during this positive half, if I fire P1, what will happen? The load will receive a supply from A to this, in this direction. Now suppose in negative half, from upper group N1 will be forward biased, and from lower group P2 will be forward biased. Now suppose in this negative half, in the second half of the supply, if I fire P2 at 0 degree, then what will happen? I'll get the supply again in the similar direction. So that means if I fire P1 for the first half at alpha equals to 0 degree, and P2 in the second half at alpha equals to 0 degree, what I'm going to get? I'll get something this type of output. So that means I'll get two positive halves if I fire P1 and then P2. Now again in the third half of the cycle, if I again fire P1, then again if I fire P2, I'll be getting only the positive halves at the output. Now suppose the frequency is to be reduced to, let us say the frequency is to be reduced to 1/4. If frequency is to be reduced to 1/4, then what I can do is from 0 to pi, that means from this point to this point, I'll fire P1, then P2, then P1, then P2. So for the first 4 halves, I'll fire P1, P2, P1, P2. And then for the next these 4 halves, I'll fire N2, N1, N2, N1. If I fire the devices in this fashion, what I'll get, for the first 4 halves, I'll get a positive supply. For the next 4 halves, I'll get a negative supply. So that means for the first 4 cycles, for the first 4 cycles, I would be getting this positive half, and for the next 4 cycles, I'll be getting this negative half. So if you compare these two waveforms, this is the supply side and this is the output side. I should write it V naught. This is a correction. Now V naught, the output is 1 cycle, whereas the input, there were 4 cycles. So basically the 4 cycles of the input are converted into one single cycle. So we can say that the output frequency is equal to 1/4 of the supply frequency. Now this is a very general case. This is a very general case. That means I have considered the value of alpha as 0 degree. But if you wish to have the complete control over the output, then what we can do is we can vary the value of alpha. Now if the load is R, then there is not a big problem. But if the load is RL, then the condition is little different. In case of RL load, there can be two cases. In case number one, the current can be discontinuous, and in another case the current can be continuous. Now whether the current will be discontinuous or continuous, it will depend upon the value of beta and the value of alpha. If the value of beta is less than pi plus alpha, this is exactly as what we learned in phase controlled rectifiers. In rectifiers we learned that if beta is less than pi plus alpha, the output current is going to be discontinuous. This is the output current. Whereas if we keep the value of beta greater than pi plus alpha, then we'll get the output current as continuous. So there would be two cases only. So in first case, we have considered this as beta. So from this point, this is the 0 point. From 0 point till this is the beta. And this is pi plus alpha. So basically this is 0, this is pi, this is beta, and this point is pi plus alpha. So in this case you can see pi plus alpha is greater than beta. So pi plus alpha is greater than beta. So this current, when this device P1 is fired here, P1 is fired at alpha. When P1 is fired here, the conduction starts. During conduction, because the load is RL, the inductor starts storing energy, and then after this point, the inductor starts releasing energy. So the conduction happens from alpha, it goes up till beta. As long as this current is flowing through the load, the thyristor P1 will not stop. Hence, up till this point beta, this device P1 will keep on conducting. So P1 will conduct from alpha to beta, and the gamma will be this. Gamma is the conduction angle. So conduction will happen from alpha to beta. Now what will happen from beta to pi plus alpha? From beta to pi plus alpha, there will be no output, as the at this time none of the devices are fired. So during beta to pi plus alpha, since there is no device conducting, so the output voltage is 0 and the inductor energy is already released, So we will get zero current at this time. So at pi plus alpha, P2 from the lower group will be fired. Then the current will flow up till this point. So we will keep on getting this kind of output, and you can see the current is discontinuous. If you wish to make the current as just continuous, here this is the time from beta to pi plus alpha is existing when the current is zero. If you wish that the current remains continuous, then you can make the value of pi plus alpha equal to beta, or you can make this value beta greater than pi plus alpha. So let us see what will be the case if beta is greater than pi plus alpha. In this case, the current will, during this time, the inductor will store the charge. Here, up till this point, this charge is not fully released, but the next thyristor is fired. So it will again start charging. So this will happen like this, and you will see the output current has become continuous. There are two cases taken for different values of inductance at the output side. In this case, the inductance is a little higher. In this case, the inductance is little low. So this will be the case when the beta is greater than pi plus alpha, we will be getting a continuous current at the output. Now, with this understanding of single phase to single phase cycloconverters, let's practice a small question. Let us try to sketch the output voltage waveform for a single phase bridge cycloconverter which is feeding an R load, and we wish to have a output frequency which is equal to 1/3 of the input frequency. Firing angle here considered as alpha. Now beta will not be applicable here because the load is R. So let us see, if the firing angle is 30° and the required frequency is 1/3, then how the output will look like. So we have considered a bridge converter. During this time, this is alpha equals to 30°. During this time, P1, P2 will work. This time output will be 0. Then P3, P2 will be P3, P4 will be fired. Then output will be 0. Then P1, P2 will be fired, and so on. So for the first three halves, we will get the positive supply. For the next three halves, we'll get the negative supply. So this dotted line indicates the output that we are getting. Now you can see this is the first cycle, then this is the second cycle, and this is the third cycle. These three cycles are converted into one cycle at the output. So we can say that the output frequency is reduced by 1/3. If you wish to find out the RMS voltage, the RMS voltage will integrate Vm square sine square omega t from alpha to pi. The periodicity will be taken as 1 by pi. So if you solve this, you get the output RMS voltage as the one given here. RMS value of load current can be calculated by just dividing this V naught R by R. Now here each thyristor conducts for 1 by 2 F naught is equal to pi radians with a periodicity of 2 pi. Therefore, RMS value of the current for each thyristor will be I naught R by 2. Basically, it is similar as the output of a half wave rectifier. So basic, because the thyristor is in one cycle, the thyristor is just conducting for pi radians. That is why the RMS current will be I naught R by 2. I think this is enough for the lecture today. In next lecture, I shall discuss about the three phase to single phase cycloconverters. Thank you.